Hello friends, welcome to Brain Amplifier, and in this video we'll be discussing about the basic cycle of a thermal power plant. The cycle is called steam and feedwater cycle, and it is the single most very important cycle of the power plant. You need to understand this cycle if you want to understand a plant. So let us start. You all must be having a basic idea of the plant, that what we do in to generate electricity. We convert water into steam at very high temperature and pressure using this boiler and some pumps. So after the boiler, the high temperature steam goes to these turbines. This is high pressure turbine, this is intermediate pressure turbine, and this is low pressure turbine. And after doing that rigorous work, the steam does that work by expanding on the turbines, by expanding on the turbine blades. And after doing that work, the thermal energy of that steam is converted into rotational mechanical energy of these turbines, and now you can connect a generator after the LP turbine and convert that rotational mechanical energy to that electrical energy. Simple. So we have to understand this cycle, how this that steam is converted from water. So we'll take the case from here. We'll start from here. The steam has, after the IP exhaust, the exhausted steam has come to LP, in the middle of the LP, and now what it will do, it will expand on both sides. And when the steam expands, its temperature and pressure will reduce with the stages. Now the turbine has multiple stages of blades. If I call it the first stage, these are blades, okay, these are surrounding this solid part, and this complete section is called the rotor of the turbine. So this is my first stage, this is second, third, fourth, fifth. Suppose I have 5-stage turbine, so these are 5 stages of the turbine. With every stage my steam does work on it, and when it work on it, it reduces its energy by reducing its temperature and pressure. So the temperature and pressure will be highest at this first stage, while the temperature and pressure of the steam will be lowest and the last stage. Now how can I increase the efficiency of this steam working on the turbine? By increasing this pressure difference. The more this pressure difference will, the higher work the steam will do on this turbine. Suppose I have pressure X here and I have pressure Y here, and then the value of X minus Y I need to increase. Okay, how I can do that? I can reduce the value of Y. I can reduce, if I reduce the value of Y, the value of X minus Y will increase. So what I do, the last stage of this turbine is connected to something called this condenser. Okay, something called this condenser, and I create a vacuum in that condenser. So due to that vacuum, the last stage of this turbine is in vacuum. That is why the difference between X and Y increases due to the reduction in the pressure of Y, and that increases the efficiency of this cycle. Okay, so why I need this condenser, why I need to condense something, what I need to do after the working on the turbine, the steam need to be condensed. Why I need to do that? Why I cannot again just heat it up again and put it into the boiler, heat it again and give it to turbines? I cannot do that because the steam here has very high volumes, and that volume is about 1600 to 700 times of water. So to pumping that much amount of steam is very difficult. Also the compression of the gases is very difficult in compared to pumping of the liquids. One more thing, there are 2 reasons. Now the third reason is I have to increase the pressure, because here I have to give a pressure on HP turbine maybe up to 150 to 300 kg. Okay, so for that I need to increase pressure, and for that I have to pump that. Okay, that is why I need to condense that steam. How I condense this? Simple, just a shell and tube type heat exchanger. This is called condenser. How does condenser look like? This is the front view of condenser. It has shell and tube arrangement. On the bottom side it has this hot valve. The condensed steam gets collected into this hot well. Now, how does this Sharon tube arrangement work? In the tubes runs my cooling water. Now the cooling water may be some river water, sea water, or any other source you have, and the steam goes into this shell arrangement. When the steam gets into contact with this cold water, it obviously get condensed. Now how so the that condensed steam gets collected into this hot well. Now how the vacuum is created inside this condenser? Suppose you have a 1 liter of container, and which is airtight 1 liter container, and you have filled some 1 liter gas into that container. Okay, I have filled 1 liter of gas into that container. Now if I condense this gas, what will happen? The volume of that gas will reduce. Suppose my volume now after reduction my volume has become 700 ml. 700 ml. Then what will be in this remaining 300 ml is vacuum. Vacuum. Okay, similarly the vacuum is created here. You have steam. Now you are condensing the steam, then the volume of that steam will decrease after condensation, and as this complete system is closed, it do not have any ingress from the atmosphere, it is a closed system. So if you will condense the steam, then naturally the vacuum will be created in the condenser, because now the steam has converted into water and volume has reduced, so in the remaining part there will be vacuum. Now there may be chances that some non-condensable gases has ingressed in the condenser, and that has not been condensed, and that will not come at the bottom part of this hot well. It will remain in this upper section, and it will kill the vacuum. And if it kills the vacuum, then my value of y will increase. Okay, I want y to be less, so that the pressure difference here increases. So what I do to suck out those non-condensable gases is attach a vacuum pump in this upper section. Now what this vacuum pump does is simply suck out that vacuum from that non-condensable gases from this upper section. After that I have CEP, that is condensate extraction pump, and simply it just has to extract that condensed water from this hot well. Now the hot well is at a vacuum, so if I have to suck something from the vacuum, it is very difficult. So I need a very high efficient pump. It is centrifugal multi-stage pump. Okay, and to create that I need it very efficient now. So what I do, I put it at a physically at a level lower than the hot well level, so that I can create a natural head for this. Now how does these pumps work, I will discuss in very brief. These centrifugal pumps have these impeller blades in the center. This is called the eye of the pump. When this impeller rotates, a vacuum is created at the eye. Okay, and you connect that eye to that source of the fluid. Okay, so if the vacuum is created, the fluid will get sucked into that vacuum, and when it gets sucked here, then after that the impellers, it goes to these impeller blades and then sent somewhere else, wherever you want to pump that. Now the power of that vacuum should be high enough so that it can suck that fluid. Okay, you got my point? Okay. So that is why we use a vertical pump for the CEP, because those are high efficient, and also we put it at a level lesser than the hot well level. After the CEP comes the CPU, that is condensate polishing unit. If there are some impurities in that water, see, we not need very pure water, because that water is going on the turbines, and I do not want my turbines are very costly and made of some good metals, mixture of molybdenum and some part of nickel also in the later stages. So I do not want them to eroded by some impurities. I do not want them to get damaged, so I need very pure water. CPU does that. CPU, it contains multiple beds of resins, and it removes any impurities. Okay, after the condensate polishing unit comes the GSC, that is gland steam condenser. and after that blend steam condenser comes this heater arrangement. Now what I want to do, I want to increase the efficiency of this cycle. So what I do, I have some water after the GSC and I want to send it to boiler. So what I can do, I can increase, before I send it to boiler, I want to increase the temperature of that feed water in steps. Okay, by if I increase the temperature, this obviously my cycle efficiency will increase, because my boiler has to do lesser work then. Okay, so how can I do that? If I want to do that in steps, I am using LP heaters, multiple, maybe 2 3 4 based on the unit. Now how does that LP heater, for heating I need a heating fluid also, and the easiest available heating fluid in the plant is steam. So what I will do, I'll heat this feed water by using the steam. Okay, so if I'll do this in steps, suppose I have a 60 degree centigrade water here, suppose I have a 60 degree centigrade water here, and I want this output of this LP heater 7, I have given name 765. If I want the output of LP heater 7 to be 70 degree centigrade, so what I can do, I can use a steam of 80 degree centigrade. I want it to 60 to 70, I can use a steam of 80 degree centigrade. Now the output here is 70. Okay, I want 80 degree centigrade steam here. Okay, now I have output here 60 degree. Now I have 70 degree centigrade feed water, and this is steam. Now that 70 degree centigrade feed water goes to LP heater 6. Now I want output of 80 degree centigrade feed water, so I can use a 90 degree centigrade steam for that. Okay, that will increase the temperature from 70 to 80. Now I want a 90 degree centigrade feed water. After LP heater 5, I can use a steam of 100 degree centigrade to increase the temperature from 80 to 90. This is just an example. Okay, the exact values are not this, those are higher than this. Now what pattern you are seeing now, the steam I need here has lesser temperature than this and this. Okay, I forgot to tell you, oh no, I told you one thing, the temperature here is highest, temperature and pressure at the first stage of this turbine is highest, while temperature and pressure reduces with the stages. So what I can do, I can extract steam from this turbine from different stages. That is, for LP heater 7 I need a lesser temperature steam, I can extract it from somewhere from the last stages of this LP turbine. Okay, I'll take a tapping from here and inject it here. Okay, for this LP heater 6 I need a steam of somewhere higher temperature than 80, so I can tap it from somewhere from the middle of this LP turbine. Okay, then for LP heater 5 I need a steam of having higher temperature than this, of 100 degree centigrade for example. Then I can extract it from somewhere at the initial stages of this LP turbine. Now the 100 degree centigrade coming from the initial stages also has higher temperature than this. I told you the pressure also reduces from this stage to this stage. Pressure is maximum here and lowest here. So pressure of this steam is highest, then of this steam is somewhere lower, and from of this steam is lowest. So now I'll discuss briefly the internal structure of this LP heater. Okay, so this is the inlet, my feed water comes here. After the GSC my feed water comes here. Okay, then it goes to this U-tube arrangement inside this heater, and in this U-tube arrangement, after this U-tube arrangement it gets out from here. So if it is my LP heater 7, then this feed water outlet goes to inlet of LP heater 6. Okay, so if the inlet of LP heater 6, it is 6 is also similar, so the inlet will come from here again. Similarly, LP heater the output of LP heater 6 goes to LP heater 5 feed water outlet, and then the outlet of LP heater 5 feed water outlet goes to deaerator. Okay, now I want to understand the how the steam comes. The steam is injected from here. Okay, steam is coming from here, and when it gets into contact with this cold feed water line, it will exchange some heat and the steam will get condensed while the feed water temperature will increase. Now that condensed steam will get collected at the bottom part of this LP heater. Now I need to drain that condensed water also, otherwise my LP heater levels will keep on increasing. So I do not want that. I need to control those levels also, so I have to keep a close eye on that. Okay, so how can I drain that? See the what we know, the pressure, the steam pressure here is maximum in LP heater 5, lesser in LP heater 6, and lowest in LP heater 7, and condenser has vacuum. So the out of this U tube also, the pressure will be highest in LP heater 5, lesser in LP heater 6, and lowest in LP heater 7. So the drain of LP heater 5 will naturally can be sent to LP heater 6. Okay, I'll put a drain line from 5 to 6, and that will send naturally the drain to 6, because the pressure is higher here and lesser here. The drain of LP heater 6 can be sent to LP heater 7 naturally. If I put a drain line from 6 to 7, naturally, because of the pressure is higher here and lesser here, the drain will go naturally here. The LP heater 7 drain goes to condenser, because here we have vacuum and here we have some pressure, so the drain naturally goes from here to here. Okay, so remember, the feed water flow is in this direction, that is from GSC to LP heater 7, LP heater 7 to 6, 6 to 5, 5 to deaerator. While my this is the feed water flow, while my drain is going in opposite direction, that is from LP heater 5 to 6 to 7 to condenser. This is feed water, this is drains, remember this. Okay. After that heating, I have a good enough temperature of that water. Now I send it to deaerator. See, these heaters now, they do not have any physical contact between steam and feed water, so these are called closed feed water heaters. Okay, while deaerator is a open feed water heater, because in this we have direct contact between steam and feed water. Okay, why it is called deaerator? Because it simply, as the name says, it deaerates the feed water. It removes any non-condensable gases, oxygen, carbon dioxide from the feed water. Why I need to do that? If I do not remove oxygen and carbon dioxide, the oxygen will react with the metals of the tubes, and it will create metal oxides, which are corrosion. Okay, which is corrosive, and it will create corrosion in the tubes. If I do not remove carbon dioxide with reacting with the metal, it will create carbonic acids, and those are again corrosive. Okay, the corrosion in this system depends on three things: the temperature and pH value and oxygen content. If I increase the temperature of the system, my corrosion will be more aggressive. If I reduce the pH value, that is I go on more on the acidic side, my corrosion will get more aggressive. If I increase the oxygen content, my corrosion will get more aggressive. Okay, so I have to remove that oxygen carbon dioxide from this feed water. How does that work? Again, I need to take some steam here, some steam and feed water. Feed water is coming from here after LP heater and getting injected from here. Okay, now the steam is the tapping of steam again has been taken from turbine. Some of the IP, maybe from IP turbine. These things depend on manufacturer to manufacturer, from where he is taking tappings, and then that steam gets injected through this pipe. Now that pipe is connected to a perforated pipe deep inside this deaerator, which is submerged into this feed water. Now this perforated pipe has holes on it, and the steam gets out from these holes and try to mix up this with this feed water. Okay, and what it'll do, it will increase the temperature of this feed water. I have generally have a baffle plate to bifurcate the deaerator in two parts. In the first part, my boiler feed water will be sprayed and it will get preheated, and after that preheated water will go into this section. In this section, the steam injected into the water will increase its temperature, and then this if I increase the temperature, the solubility of my gases will decrease, because there is one law called Henry's law. What Henry's law says, that the soluble amount of dissolved gases into a liquid will be proportional to its partial pressure. Okay, and Dalton's law says that the total partial pressure of some mixture will be the sum of the partial pressure of different gases or liquid, whatever it contains. Okay, so according to Henry's law, the amount of my oxygen CO2 will be proportional to the partial pressure of those oxygen CO2. So if I reduce that partial pressure, I can reduce the solubility of those gases into water. There are two ways to reduce that partial pressure. One is I increase the temperature of this water. By increasing the temperature, I'll increase the vapor pressure of that water. What is vapor pressure? I'll discuss it in very briefly. Vapor pressure is in nothing but, if you want to keep that liquid into liquid state, you have to inject some pressure from upside. In normal atmosphere does that work. Okay, so that pressure is called the vapor pressure. If I reduce this pressure, my water will get converted into vapor. So if I'll heat up this water, I need to inject more force in it to keep it in liquid state. That is, my vapor pressure will increase. Okay, but my oxygen and CO2 will get out of it due to the reduction in partial pressure. Also, if I reduce the temperature of this outer atmosphere in deaerator, I can again move them oxygen CO2 out of this liquid. So if if I am increasing the temperature of this liquid, my oxygen and CO2 are getting out of it, and then I have a air vent here, and those get out through this air vent. So I have deaerated water after this deaerator. Now I have this boiler feed pump. It is the single most entity which is consuming maximum auxiliary which is resulting maximum auxiliary consumption in a unit. It may consume up to 10, 11, 12, 15 megawatts of power. That is equivalent to supplying a town. Okay, so what we nowadays trend is of TDBFP instead of MDBFP. MDBFP is motor driven boiler feed pump. TDBFP is turbine driven boiler feed pumps. To reduce the auxiliary consumption, what we do, we put a turbine into this pump, and that turbine is rotated through the steam. The steam may be tapped out from some stage of turbine, and it rotates the turbine, and that make the pump work. Okay, now the BFP has to be very powerful to create that much amount of pressure, so that my feed water gets from here to here and circulate into the boiler, and after that also goes to the HP turbine, does work on it. I mean from here to here to here to here, for the complete cycle up to here, up to CEP, you need to create very high pressure. Okay, after that comes my HP heaters. HP heaters are similar to LP heaters. My feed water goes to HP heater 3, then HP heater 2 to HP heater 1. Similarly, my drain of HP heater 1 goes to HP heater 2, HP heater 2 drain goes to HP heater 3, and HP heater 3 drain goes to deaerator. Remember, these are called LP heater because the extraction of steams was from LP turbines to heat them up, while these are called HP heaters because the extraction of steam will be from HP or IP turbine. Okay, the working will be very similar. Some extraction will be coming of steam here, and there will be some U-tube arrangement here. Feed water will be passing through this that U-tube arrangement and going to this boiler, and my drains will be coming here to deaerator. Drains of LP heaters are thrown to condenser, while the drains of HP heaters are thrown to deaerator. After this heaters, my feed water goes to boiler section. This complete is my boiler section. In boiler I have economiser. It is called here I burn my fuel, and the flue gases goes from here to here. This is first pass of boiler. This is second pass of boiler. Here the temperature of that feed water increased using the temperature of those flue gases. And after that economiser, I won't discuss the boiler section into detail because it is a single entity to be discussed separately. Then after economiser, my water goes to boiler drum. If it is a subcritical unit, in supercritical you may not find a boiler drum. That is a separate issue. After the boiler drum, my feed water goes to the through those downcomer to bottom ring header, and then through this furnace. Inside the furnace there are water walls. Again it is heated in the furnace and goes to again boiler drum. After even after getting higher temperature in the furnace, my water contains some particles of moisture. So to remove that moisture particles, I have to superheat it. So I send it to superheaters. They may be in multiple stages, that is low temperature superheaters, platen superheater, final superheater. So after superheating the steam, my steam is totally moisture free, because I do not moisture to get injected on turbines, because that may corrode the turbine metal. So after that, superheated steam is thrown to turbines. Now it does work on the turbines by expanding on the stages. Why the shape is because the why this shape? Because the size of the stages, the turbine blades keep on increasing with the stages, because the volume of the steam will increase. Now you need to contain more volume of steam, so you need larger size, so the sizes keep on increasing. After HP turbine, my the temperature and pressure of the steam has been reduced, so I can so it again can contain moisture, so I need to again reheat it. So for that I again sent it to boiler section. In boiler I have reheaters. What those reheaters do, they just increase the temperature of that steam, but they do not change any make any change in the pressure. So after again, if I have somewhere 570 degrees centigrade temperature here, and maybe about 350 degrees centigrade temperature at the HP outlet, these are just example, this is just example, then the reheater will again create the temperature of 570 degrees centigrade, but the pressure will be very less. Then that low pressure high temperature steam is sent to the IP turbine. Now the pressure is very less, so the volume of the steam will be higher, so the IP turbine size will be larger than HP turbine, because here I need to contain higher volume of steam. Okay, then after the working on the IP turbine blades, my steam goes to this LP turbine. So the cycle has been completed. I'll brief it again in very brief. From LP turbine to condenser, from condenser to condensate extraction pump, then condensate polishing unit, gland steam condenser, then we increase the temperature in heaters. After heaters we deaerate it with the deaerator, then using the boiler feed pump. From deaerator works as a reservoir also. I extract that and send to HP heaters. Again I increase some temperature, then send it to economiser, and here again I increase the temperature of feed water by using the flue gases. Then after economiser, send it to boiler drum if it is a subcritical unit. Then through the downcomer it comes to bottom ring headers, then it again goes up to boiler drum using this water walls. Then from boiler drum I say again need to superheat it to remove moisture. After superheater, it does work on the HP turbines, reduces its pressure and temperature, again increase temperature in the reheater, does work on IP and LP turbine. Please friends, if you like the video, like it, give a thumbs up, share it, and please subscribe to my YouTube channel. Hit the bell icon so that you can keep updated yourself with the new videos. And if you want to know about any other cycle of the power plant, or any of these components in detail, or any other thing about the power plant, you can just comment below in the comment section. Okay, bye for now. Thank you.